Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs. M.Sc. Applied Statistics, MSCAST Semester 2. MST 016 Statistical Inference. Block-1 Fundamentals of Statistical Inference. Unit-1 Foundation of Sampling Distributions. 1.1 Introduction. In many situations, we have to extract some information from all the elements or items of a large population in general. It may be time-consuming and expensive. Also, if the elements or items of a population are destroyed under investigation, then the information gathered from all the elements is not making sense because all the elements will be destroyed under investigation. Therefore, in most of the cases in daily life, business and industry, the information about the population is gathered through a random sample. The results of a properly taken sample enable the investigator to arrive at generalizations that are valid for the entire population. The process of generalizing sample results to the population is called statistical inference. For drawing inferences about the population characteristics, known as parameters, on the basis of a sample, the sampling distribution helps us. This unit, as the title, is devoted to explaining the fundamentals required to understand the sampling distribution as well as statistical inference. This unit is divided into 8 sections. Section 1.1 is introductive. In Section 1.2, we define the basic terminology used in statistical inference, such as population, sample, statistic, parameter, simple random sampling, estimator, and estimate, etc. The concept and role of sampling distributions in statistical inference are described in Section 1.3. In Section 1.4, we explored the concept of standard error. The most important theorem, central limit theorem, and law of large numbers of statistics are described with their applications in Sections 1.5 and 1.6, respectively. The unit ends by providing a summary of what we have discussed in this unit in Section 1.7, and the terminal questions and the solution of the exercises are given in Sections 1.8 and 1.9, respectively. In the next unit, we shall discuss the sampling distributions of proportions as well as variances. Expected learning outcomes. After studying this unit, you should be able to define statistical inference. Define the basic terms as population, sample, parameter, statistic, estimator, estimate, etc. used in statistical inference. Interpret the concept of the sampling distribution. Explain the concept of standard error. Describe the most important theorem of statistics, central limit theorem. Apply the central limit theorem in the real world. Explain the concept of the law of large numbers with its application, and determine the adequate sample size required for a sample survey. 1.2 Basic terminology. Before starting the discussion on the sampling distribution/statistical inference, you should understand the basic definitions of some of the important terms, which are very helpful to understand the fundamentals of statistical inference. Population. In a general sense, population means a group of people who live in a particular geographical area, or the entire group of individuals or objects that share a common characteristic and are of interest to a researcher. For example, the group of people who live in New Delhi, the group of teachers working in IGNOU, students enrolled in the MSCAST program in IGNOU, etc. In statistics, a population has a much broader meaning. A population is an entire group about which some information is required to be ascertained. In statistics, population need not consist only people but also the group of elements or units under consideration by the analyst. Thus, a population is the collection/group of individuals/items/units/observations under study. For example, the collection of laptops of a company, the group of universities who are offering M.Sc in applied statistics, the learners in a counseling session. etc. are considered as populations in statistics. In statistical inference, a population need not consist only of people or units. We can also define it as a population is a group of measurements in the quantitative or qualitative form of the characteristic under study. For example, salaries of employees in a company, weights of newly born babies in a hospital, hemoglobin levels of patients, marks of learners in a paper, the diameter of ball bearing produced by a company, etc. The total number of elements/items/units/observations in a population is known as population size and is denoted by N. The characteristic under study may be denoted by X or Y. Sample. In general, collecting the information from all units of a large population is time-consuming and costly. Also, if the units of a population are destroyed under investigation, then gathering the information from all the units does not make sense. For example, test the blood of a patient, test the quality of crackers, etc. In such situations, a small part of the population is selected from the population, which is called a sample. Thus, the sample can be defined as a sample is a part/fraction/subset of the population. For example, a syringe full of blood taken from the vein of a patient is a sample of all the blood in the patient's circulation at the moment. Similarly, a group of 26 learners of the MSCAST is a sample of the population of learners of the program. The number of units selected in the sample is known as sample size and it is denoted by N. It is extremely important to choose a sample that is truly representative of the population so that the inferences derived from the sample can be generalized back to the population of interest. Sample mean and sample variance. Statistical inference is a technique of drawing conclusions about the population from data, sample. It is based on the assumption that the sample should be random. We have various techniques to select a random sample. In MST 013, Survey Sampling and Design of Experiments, you have studied various sampling methods so that we can maintain the randomness. In statistical inference, we use simple random sampling because for randomness it is sufficient. Let us look at the sampling. Simple random sampling. Simple random sampling is the simplest and most common method of sampling used in statistical inference. In simple random sampling, the sample is drawn in such a way that each unit of the population has an equal and independent chance of being included in the sample. If a sample is drawn by this method, then it is known as a simple random sample or a random sample. The simple random sample of size N is denoted by X, X12N or Y, Y12N, and the observed value of this sample is denoted by 12N, 12NX, X or Y, Y. Some authors use 12NX, X to represent the random sample instead of X, 12N, but throughout the course, we use capital letters to represent the random sample, that is, X12N or Y12N. In simple random sampling, elements or units are selected or drawn one by one, therefore it may be classified into two types. 1. Simple random sampling without replacement, SOS. In simple random sampling, if the elements or units are selected or drawn one by one in such a way that a unit drawn at a time is not replaced back to the population before the subsequent draws, is called SOS. In this sampling, the same unit cannot appear more than once in the sample and the probabilities of each selection are not the same because we did not replace each selection. 2. Simple random sampling with replacement, SRSWR. In simple random sampling, if the elements or units are selected or drawn one by one in such a way that a unit drawn at a time is replaced back to the population before the subsequent draw is called SRSWR. In this method, the same element or unit can appear more than once in the sample and the probability of selection of a unit at each draw remains the same. Now a question may arise: if we draw a sample of a specified, given, size from a population, then how many samples are possible? To understand the answer of the same, we should know two things: first, whether the order of the unit in the sample matters or not, and second, whether the drawn unit in the sample is replaced before the subsequent draw or not. Know the basis of this. The following 4 cases may arise. Ordered sampling with replacement, unordered sampling with replacement, ordered sampling without replacement, unordered sampling without replacement. To see the effect of ordering and replacement on the number of samples, we considered an example in which the size of the population is very small. Suppose the statistical discipline of a university has 4 typists, A, B, C and D, constitute a population. We select a sample of 2 typists from this population of typists for typing a manuscript. We now discuss how many samples may be possible in different cases. Ordered sampling with replacement. In this case, order matters. The order of selecting the typists in the sample is important. It means that if we select typist A first and then B, I, E, AB, differs from selecting B first and then A, I, E, B, A, and each of these samples is regarded as a different possible sample that can be selected from this group of typists. We replace the unit. A unit drawn at a time is replaced back to the population before the subsequent draw. With replacement means A sample of selecting the typist A and then A again, AA, is possible. In this case, the total number of possible samples will be 16, which are listed below. AA, repletion allows, CA, order matters, OBCB, order matters, ACCC, repletion allows, ADCD. BA, order matters, DA, order matters, BB, repletion allows, DB, order matters, BCDC, order matters, BDDD, repletion allows. In this case, we can determine the total number of possible samples of any size, n, that can be selected from a population of any size, n, using the following formula. Total number of possible samples equals nn. Dot. This, ordered sampling with replacement, is also known as theoretical sampling, and it is used to develop the theories of sampling distribution. This case is also known as SRSWR. Unordered sampling with replacement. In this case, order does not matter. The order of selecting the typists in the sample is not important. It means that if we select typist A first and then B, I, E, AB, is the same as selecting B first and then A, I, E, B, A. These samples are considered as one and are not considered separate samples. We replace the unit. A unit drawn at a time is replaced back to the population before the subsequent draw. With replacement means a sample of selecting the typist A and then A again, AA, is possible. Ordered sampling without replacement. In this case, order matters. The order of selecting the typists in the sample is important. It means that if we select typist A first and then B, I, E, AB, differs from selecting B first and then A, I, E, B, A, and each of these samples is regarded as a different possible sample that can be selected from this group of typists. We do not replace the unit. A unit drawn at a time is not replaced back to the population before the subsequent draw. This means that the same participant can never be sampled twice. So, the samples of A, B, B, C, C and D from the population in this example are not possible. With replacement means a sample of selecting typist A and then A again, AA, is possible. Unordered sampling without replacement. In this case, order does not matter. The order of selecting the typists in the sample is not important. Order does not matter. It means that if we select typist A first and then B, I, E, AB, is the same as selecting B first and then A, I, E, B, A. These samples are considered as one and are not considered separate samples. We do not replace the unit. A unit drawn at a time is not replaced back to the population before the subsequent draw. This means that the same participant can never be sampled twice. So, the samples of A, B, B, C, C and D from the population in this example are not possible. With replacement means a sample of selecting the typist A and then A again, AA, is possible. We can determine the total number of samples when order does not matter, and repetition is not allowed using the following formula. Total number of possible samples equals NCN. We may select diverse samples. But in practice, order does not matter because we do not care about the order in which individuals are selected. Also, we usually do not allow one individual to be chosen twice. Therefore, we often do the unordered sampling without replacement. Therefore, it is also called experimental sampling. However, in statistical inference, ordered simple random sampling with replacement, commonly called SRSWR, is used to develop the theory of statistical inference. On the other hand, in a large population, the probability of selecting the same individual twice is negligible, and it can be demonstrated that the results obtained from sampling with replacement are very close to the results obtained using sampling without replacement. The main advantage of sampling with replacement is that the sample observation will be independent, and this simplifies the analysis. Example 1. There are 5 sales associates at a car showroom. The number of cars they sold last week is as follows. Sales associate cars sold. Vihan 2. Rohan 5. Ritika 4. Hassan 6. Anita 10. A researcher selected a sample of 2 associates. How many samples of size 2 are possible with replacement, order and replacement allow? Also, write them. Solution. Here, we are given that population size equals n equals 5. Sample size equals n equals 2. Since we know that all possible samples of size on taken from a population of size on with replacement, order and replacement allow, are nn. Therefore, possible samples in our case nn equals 52 equals 25. These 25 samples are given in Table 1.1 along with the car sold. After understanding the concept of population, sample and how many samples are possible in different cases, let us move to the next concept. Parameter. The characteristics of a population can be described with some measures, such as population mean, variance, etc. These measures are known as parameters of the population. Thus, we can define a parameter as a parameter or population parameter is a numerical value that summarizes or measures or represents a specific characteristic of an entire population. The parameters are derived from data collected from the entire population and taken as fixed constants. For example, suppose the program coordinator of the MSCAST program calculates the average marks of the learners in their graduation by considering all the learners, then the obtained average marks is a parameter, because it is based on all the learners of the MSCAST program. Similarly, population variance, population coefficient of variation, population correlation coefficient, etc. are all parameters. Population parameters usually denoted by Greek letters, such as the population mean and variance are represented by Greek letters mu and sigma 2, respectively. Generally, the parameters of a population are typically unknown and are estimated from sample data. We know that the population of measurements such as height, marks, etc. can be described with the help of distributions such as normal, Poisson, etc. and the distribution is fully determined with the help of its constants such as, in case of a normal distribution, we need to know mu and sigma 2 to determine the normal distribution. In case of Poisson distribution, we need to know lambda, etc. These constants are also known as the parameters. Statistic. As a parameter describes the characteristic of the population in a similar way, a statistic describes the characteristic of the sample. We can define a statistic as a sample statistic or statistic is a numerical measure that summarizes or describes a characteristic of a sample. The statistic is calculated using sample data. For example, suppose the program coordinator of the MSCAST program calculates the average marks of the learners in their graduation by selecting some learners of the program sample, then the obtained sample average marks is a statistic, because it is based on the sample of the learners of the MSCAST program. Similarly, sample variance, sample coefficient of variation, sample correlation coefficient, etc. are all statistics, plural of statistic. The statistic is usually denoted by Roman/Latin letters, such as the sample mean and variance are represented by X and S2, respectively. Generally, the statistic is used to estimate the population parameter. Estimator and estimate. Generally, population parameters are unknown and the whole population is too large to find out the parameters due to cost and time constraints. In such situations, we take a sample from the population. Since the sample drawn from a population always contains some information about the population, therefore, we guess or estimate the value of the parameter under study based on a random sample drawn from that population. A statistic that is used to estimate an unknown parameter is known as an estimator. An estimator is a function of the data in a sample. Common estimators are the sample mean and sample variance, which are used to estimate the unknown population mean and variance. The estimator itself is a random variable because it is a function of the random sample data. Its value varies from sample to sample due to the randomness inherent in the sampling process. A particular value of the estimator based on the observed value of the sample is known as an estimate of the parameter. For example, let us suppose that you as a pharmacologist want to test a new systolic blood pressure (SPP) medicine. For that, you select a random sample of 100 SPP participants to try the medicine and prescribe the medicine for 1 month. After 1 month, you measure the SPP of the participants. Then, you calculate the mean of the SPP measurements. Suppose the mean SPP is found as 125 mm Hg. Then sample mean is called the estimator and this number, 125 mm Hg, allows you to estimate that a more general population is likely to maintain 125 mm Hg SPB while taking the medicine. Another example is in regression analysis, where the least squares estimation method is used to find the line of best fit. The regression coefficients obtained from this method are the estimators, while the predicted values on the line of best fit are the estimated values for the dependent variable. In this course, we use capital letters for the estimator and small letters for the estimated value. For example, we represent the estimator sample mean X and its particular value as X as an estimate. In general, the estimator is denoted by Tn equals Tx1, x2, xn, when denotes the sample size, and the estimator T is a function of the random sample x1, x2, xn. Now, you check your understanding of the above discussion by answering the following self-assessment questions. After understanding the concept of basic terminology, you are now ready to learn the main concept of this unit, that is, sampling distribution. Let us discuss it in the next section. 1.3 Introduction to Sampling Distribution. As we have discussed in section 1.1, if the population is too large or the units or items of the population are destructive in nature or there are limited resources such as manpower, money, etc., then it is not possible practically to examine every unit of the population to obtain the necessary information or characteristics/parameters of the population. For example, suppose we want to know the average life of electric LED bulbs of a certain brand which are manufactured by a company. The company manufactures a lot of bulbs, say 5,000 per day. Then gathering information about the average life of all the bulbs does not make sense because the bulbs are destroyed under investigation. In another example, if we want to know the average income of the persons living in a big city, then collecting the information from each person is very much time and manpower consuming. In such situations, one can draw a sample from the population under study and utilize sample observations to extract the necessary information about the population. The results obtained from the sample are projected in such a way that they are valid for the entire population. Therefore, the sample works like a vehicle to reach, drawing, valid conclusions about the population. Thus, Statistical inference can be defined as the process of projecting the sample results for the whole population is known as statistical inference. For drawing the inference about the population, we analyze the sample data, that is, we calculate the value of a sample statistic such as the sample mean, sample proportion, sample variance, etc. Generally, if we want to draw inference about the population characteristics such as population mean, we use sample mean, about population variance we use sample variance, etc. For example, suppose a researcher of health science wants to know the average cholesterol levels of the persons living in a city. For practical reasons, he cannot reach out to each and every person in the city. So, he randomly selected 10 individuals from the same city and measured their cholesterol levels. Now, if we are using this sample to make an inference about the population's average cholesterol level, then we say that the sample average cholesterol level 195 mg/dl is an estimate of the average cholesterol level of the persons living in this city, population. However, we do not know the precision, the estimate is accurate or not, of the estimate because the actual cholesterol level of the persons in the city is unknown. If another random sample of 10 individuals is selected and measured their cholesterol levels, shown in column 3 of table 1.1, then we get the average, mean, cholesterol level of these selected individuals is 210 mg/dl. This is different from the sample I because it contains different individuals, which have different cholesterol levels. Thus, if we are using this sample mean to estimate the population mean, then we get a different estimate of the average cholesterol level for the whole population. If other samples of 10 individuals are selected, it is unlikely that exactly the same mean would be observed, therefore, we may expect different estimates of the population mean every time. Now the following questions may arise. How can we tell which sample gives the best estimate of the population? Parameter: how well does a sample describe its population? What is the probability of selecting a sample with specific characteristics? These questions can be answered once we establish the sampling distribution of the statistics such as mean, variance, proportion, etc. The sampling distribution of a sample statistic is important because it enables us to draw conclusions about the corresponding population parameter. For a better understanding of the concept of the sampling distribution, we consider a population of very small size so that we can easily obtain unknown population parameters, say, mean, mu, and standard deviation, sigma, using all population observations, and see how the sampling distribution helps us to draw a conclusion about the population. Consider a small production industry which has 5 employees. From the above figure, we observe that the monthly salary of the employees does not follow an own distribution and it is left skewed. Let us assume that we do not know the average salary of the employees. So we decide to estimate the population mean on the basis of a sample of size n equals 2. There are n equals 52 equals 25 possible simple random samples with replacement of size 2. All possible samples of size n equals 2 are given in the second column of table 1.4. We also calculate the mean of each sample which are given in the last column of the same table. Look at the screen table 1.4, calculation of sample mean from the above table. We can see that the value of the sample statistic, sample mean, varies from sample to sample, and out of 25 samples there is no sample whose mean is equal to the population mean. It means that out of 25 samples no one estimates the population mean exactly. So, what do we do now? The sampling distribution helps us in such situations. We now try to understand the concept of it. Since the sample mean varies from sample to sample, therefore, it is treated as a random variable. As you have studied in MST 012, a random variable has a distribution, so the sample statistic, sample mean, has a distribution. To obtain the distribution of a statistic, sample mean, we arrange the values of it in ascending or descending order and calculate the frequency of each value as shown in table 1.5. We can also obtain the probability distribution using the relative frequency approach of probability described in MST 012 of the occurrence of each value as calculated in the last column of table 1.5. So the arrangement of all possible values of the sample mean with their corresponding probabilities is called the sampling distribution of the mean. Thus, we can define the sampling distribution in general as follows as the probability distribution of all possible values of a sample statistic that would be obtained by drawing all possible samples of the same size from the population is called the sampling distribution of that statistic. As the probability distribution such as normal, Poisson, binomial, etc. allows us to gain an understanding of the summary, mean, ST, etc. likelihood and probabilities of different values occurring in the outcome. In a similar way, the sampling distributions are probability distributions that do the same job. The sampling distribution of the sample means itself has mean, variance, etc. factors that influence sampling distribution. The form of sampling distribution depends on the following factors: the distribution of the population, the statistic being considered, the sampling procedure employed, and the sample size used. In the above example, you saw that when the population size is 5, there are only 25 and 125 samples of size n equals 2 and 3, respectively. In more realistic situations, when the population is large, then the number of possible samples increases dramatically. For example, when the population has 1,000 units, then there will be 1,000, 10 lakh equals possible simple random samples of size 2, and it is virtually impossible to actually obtain every possible random sample. Fortunately, it is possible to determine exactly what the distribution of sample means looks like without taking hundreds or thousands of samples. A mathematical proposition known as the central limit theorem provides a precise description of the sampling distribution of the sample mean. It is now time for you to try the following self-assessment question to make sure that you understand the sampling distribution. 1.4 Concept of standard error. In section 1.3, we describe the sampling distribution of a statistic, mean, and observe that the mean of the sampling distribution of mean is equal to the population mean. But in the real world, the population sizes are too large, and you see that when the population size is large, then the number of possible samples increases dramatically, and it is virtually impossible to actually obtain every possible random sample and then observe the sampling distributions. In such situations, we draw a random sample from the population to draw inferences about the population parameters and use the concept of theoretical sampling distribution. For example, consider the example of estimating the average cholesterol levels of the persons living in a city. Due to cost and time constraints, the researcher selected 10 individuals randomly from the same city and obtained the average, mean, cholesterol level of these selected individuals was 195 mg/dl. Can you expect that it is somewhere close to or equal to the average cholesterol level of the whole population? I think the answer is no. Then the question may arise, how can we judge that an estimate observed from a single sample is a reliable estimate of the population parameter? How can know the precision, the estimate is accurate or not, of the estimate when it is not possible to compute the exact value? The standard error does such jobs for us. It measures how far the sample mean, average, of the data is likely to be from the true population mean. The standard error provides a measure of how much distance is expected on average between a sample mean and the population mean. It gives the accuracy of a sample mean by measuring the sample-to-sample variability of the sample means. We now formally define the standard error, SE, as the standard deviation of a sampling distribution of a statistic. Mean, proportion, standard deviation, is known as standard error. The standard error is not denoted by any symbol, whereas it is denoted by its abbreviation SE. The standard error is a standard deviation of the sampling distribution, so it is serving the same two purposes for the sampling distribution as the standard deviation of the data, which are listed as follows. 1. The standard error provides a measure of how much discrepancy is expected from one sample to another. When the standard error is small, then all of the sample means are close together and have similar values. If the standard error is large, then the sample means are scattered over a wide range and there are major differences from one sample to another. 2. Standard error measures how well an individual sample mean represents the entire distribution. Specifically, it gives an indication of the reasonable deviation that can be expected between a sample mean and the population mean. The standard error is an extremely valuable measure because it specifies precisely how well a sample mean estimates its population mean, that is, how much error you should expect. It makes us able on the average, between sample mean and population mean. However, you do not expect a sample to provide a perfectly accurate picture of the population. There is always some discrepancy, or error, between a sample statistic and the corresponding population parameter. Now we are able to calculate exactly how much error to expect. Applications of standard error. Standard error plays a very crucial role. 1. The standard error is used to find the accuracy or precision or reliability of the sample estimate of a population parameter. The precision of a sample estimate can be defined as the reciprocal of the standard error of the statistic. We can calculate the precision as precision equals 1 upon standard error of the estimate 2. It is used to construct confidence intervals, C, within which the population parameter may be expected to lie with a certain level of confidence. The standard error also determines the probable limits or confidence limits. We will discuss confidence intervals in more detail in subsequent units. 3. Standard error is also used to test whether the difference between the sample statistic and the population parameter is significant or is due to sampling fluctuations. It means that the standard error is also applicable in the testing of hypotheses. We will discuss testing of hypotheses in more detail in the last block of this course. Since the precision is reciprocal to the standard error, we try to decrease it. 1.6 Law of large numbers. We have already discussed in section 1.2 of this unit that the population parameters are generally unknown, and for estimating parameters, we draw all possible random samples of the same size from the population and calculate the values of sample statistics such as sample mean, sample proportion, sample variance, etc. for all samples, and with the help of these values we prepare the sampling distribution of that statistic, which helps us to draw inferences about the population parameters. But in the real world the population size is too large, and you see that when the population size is large then the number of possible samples increases dramatically, and it is virtually impossible to actually obtain every possible random sample and then observe the sampling distributions. In such situations, we use the concept of theoretical sampling distribution such as the central limit theorem, and we draw a random sample from the population to draw inferences about the population parameters. A very crucial question then arises: using a random sample of finite size, can we make a reliable inference about population parameters? The answer is yes. Reliable inference about population parameters can be made by using only a finite sample, and we shall demonstrate this by law of large numbers. The law of large numbers is a powerful principle that helps statisticians and analysts make sense of data. After understanding how it works and how it applies to real-world situations, you can make better decisions and draw more accurate conclusions from your data. The law of large numbers was initially known as the Golden Theorem or Bernoulli's theorem. It was first coined by the Swiss mathematician Jacob Bernoulli in 1713. The theorem later became known as the law of large numbers. There is also a more general version of the law of large numbers for averages, proved more than a century later by the Russian mathematician Pafnuty Chebyshev. This law of large numbers can be stated in words as: the law of large numbers states that as a sample size increases, its mean gets closer to the average of the whole population. In other words, as the sample size increases, the average of the observed results will become more and more representative of the true value. This is the same intuition behind the idea that if we collect more data, our sample of data will be more representative of the population. Here, try to understand the law of large numbers in action with the help of an example. Suppose the distribution of the weight of all the young men living in a city is close to a normal distribution with a mean weight of 65 kilograms and a standard deviation of 5 kilograms. To understand the law of large numbers, we calculate the sample mean weight, x, for varying sample sizes n equals 1, 2, 3. Figure 1.10 shows the behavior of the sample mean weight x of men chosen at random from this city. The graph plots the values of x along the vertical axis and sample size along the horizontal axis as sample size varying n equals 1, 2, 3. First, we start a sample of size n equals 1, that is, we select a man randomly from the city. Suppose the selected man has a weight of 70 kilograms, therefore, the line of the graph starts from this point. His process will continue. From the graph, We can see that the mean of the sample changes as we make more observations. Eventually, however, the mean of the observations gets closer and close to the population mean of 65 kg as the sample size increases. Hence, from figure 1.10, we can observe that every additional data point gathered has the potential to move the sample to the true population mean. We use the law of large numbers in a variety of fields including statistics, market research, finance, healthcare, insurance, engineering, etc. Here we mention some examples of the use of the law of large numbers. 1. In market research, let us suppose you are working for a marketing company, and you want to know what percentage of people in a certain city prefer your brand of mobile. It is not possible for you to survey every single person in the city, so you take a random sample of 100 people and ask them which brand of mobile they prefer. If you find that 40% of them prefer your brand, does that mean that 40% of the entire population prefers your brand? Not necessarily. There is always a chance that your sample was biased in some way. However, if you were to take a larger sample, say, 10,000 people and found that 45% of them prefer your brand, that would be a stronger indication that a majority of the population really does prefer your brand. And if you were to take an even larger sample, say, 1 lakh people and found that 48% of them prefer your brand, that would be an even stronger indication that your brand is really popular in the city. 2. In financial analysis, we can also use the law of large numbers. For example, suppose you are a stock analyst and you want to know the average rate of return for a certain stock. You could calculate the rate of return for a small sample of investors and get a rough estimate, but it would not be very accurate. However, if you take a larger sample of investors to calculate the rate of return, you will get a more accurate estimate of the true rate of return. 3. Similarly, the law of large is also used in medicine to study the effectiveness of treatments. If you want to know whether a certain medication is effective for a particular condition, then you could study a small sample of patients and get a rough idea. However, if you study a larger sample of patients, you would get a more accurate estimate of the effectiveness of the medication. After studies where we can use the law of large numbers, we should note the following important points. The law of large numbers does not tell that the sample mean will always reflect the true population characteristics, especially for small samples. If a given sample mean deviates from the true population mean, then the law of large numbers does not guarantee that successive samples will move the observed average toward the population mean. I hope you have understood the concept of the law of large numbers and how you can apply it to real-world situations. Hence, you can make better decisions and draw more accurate conclusions from your data. With the help of the law of large numbers, we can also determine the minimum sample size to get a reliable inference about the population. This law states that for any two arbitrary small numbers and n where epsilon greater than 0 and 0,1 less than eta less than, there exists an integer sigma equals epsilon eta 2 to n such that if a random sample of size n or larger is drawn from the population and calculated the sample mean, x, for this sample, then the sample mean, x, arbitrarily close to the population mean mu, where sigma 2 is the finite variance of the population. In statistical, inference is called margin of error and 1, n is called confidence level. 1.7 Summary. In this unit, we have covered the following points. The statistical procedure which is used for drawing conclusions about the population parameter on the basis of the sample data is called statistical inference. A population is a group of measurements in the quantitative or qualitative form of the characteristic under study. A parameter or population parameter is a numerical value that summarizes or measures or represents a specific characteristic of an entire population. A sample statistic or statistic is a numerical measure that summarizes or describes a characteristic of a sample. Any statistic used to estimate an unknown population parameter is known as estimator, and the particular value of the estimator is known as estimate of the parameter. The probability distribution of all possible values of a sample statistic that would be obtained by drawing all possible samples of the same size from the population is called the sampling distribution of that statistic. The standard deviation of the sampling distribution of a statistic is known as standard error. The most important theorem of statistics is the central limit theorem, which states that the sampling distribution of the sample means tends to a normal distribution as the sample size tends to large, n greater than 30. The law of large numbers states that as a sample size increases, its mean gets closer to the average of the whole population. In other words, as the sample size increases, the average of the observed results will become more and more representative of the true value. Thank you for watching. We will see you in the next video with the next chapter.